This is example 3a of ZTransform. In this example, we're interested to find again the output yn. In particular, we want to examine both the steady state and transient response. We're given the following difference equation to describe the system. Yn equals to 0.5 times yn minus 1 plus xn. Let's draw a block diagram to describe this system. It looks like this. This is x of n. It becomes yn. And since we need a delayed version, we will introduce the block delay here, z minus 1. So therefore this is yn minus 1. And now we multiply by 0.5. So at the output is 0.5 times yn minus 1, and we sum together. So this is plus and plus. So therefore the output is xn plus 0.5 yn minus 1. You'll learn how to draw this very simple block diagram next time, but you can see now why this block diagram represents the difference equation. The only thing is the z minus 1. This is just a block to indicate that whatever comes in is delayed by one sample. This triangle represents a multiplier, so it's 0.5 times yn minus 1. The input given to us is this. So this is a causal signal existing only on the right hand side, n equals to 0, 1, 2, 3 onwards, and it is minus 1 to the power of n. So it will alternate between minus 1 and plus 1. So in fact, you can think of this as a signal that changes pi radian every sample. So this is actually the highest frequency signal that you can use for a discrete time signal, because at every sample it changes by pi, because it goes from 1 to minus 1, which is the same as moving pi, and from minus 1 back to 1 again is again pi. So it is pi radian per sample. Alright, now we want to find yn, so we can of course convolve, but in this example we're not going to use convolution because you cannot convolve because this is an infinite signal. So what do? We take this approach, which is to take the ZTransform. So we take the ZTransform of xn, so xn become xz, yn become yz, 0.5 remain a constant, yn minus 1 becomes z minus 1 yz. Okay, so that's the trick we use again. Remember that the ZTransform property is when we take ZTransform of a constant multiplied by yn minus 1, the constant goes outside, yn minus 1 becomes yz. To take care of the minus 1 is z minus 1. We then move all the y's on one side in preparation so that we can do this to get the transfer function. Therefore, the transfer function is simply 1 over 1 minus 0.5 z minus 1. But if you do not like negative powers of z, then simply this is the same as z minus 0.5. So immediately we can see that a 0 occurs at z equals to 0 and a pole occurs at z equals to plus 0.5. So when we are seeing the ZTransform in positive powers of z, it is very obvious where are the poles and 0. It's not so obvious in the negative powers of z. Let's continue. Now we are given that xn is minus 1 to the power of n, un. Then using the lookup table, this is the ZTransform of the signal. And we use the convolution in time is equals to multiplication of the transfer function in the z domain with the input in the z domain. And then what we get is simply this equation over here. So we now have y of z in the Z domain. So what we really need to do is to convert inverse Z transform to get y of n. But you know that we do not have this representation. What we need to do is by partial fraction to convert this into small parts like this, which have a lookup table. So what we are in this example, well, if you do not know how to do the Z transform, please revise. In this example, I'm just going to use the MATLAB to show you. We'll deal with this equation. The numerator is 1, the denominator is 1 half and minus half in descending powers of Z. So because they're in descending powers of Z, we have the numerator as 1 and the denominator as 1 half and minus half. And we send this to the residual Z to get the RPK using MATLAB. Okay, so we are using RPK. Let's see what's the MATLAB answer now. So we have R is 2 over 3 and 1 over 3. P is minus 1 and half. K is 0. These values are here. So it's 2 over 3 and 1 half and minus half in the RPKs. So what we then do is that this definitely have a Z inverse Z transform, and the answer is here. Now, once we have the answer, of course, then we can plot. So what I want to show you is that as n tends to infinity, what will happen to half to the power of n? So this term goes to 0. So we call this the transient term, the transient response of the system. And in this figure, this plots the transient response. So notice that it becomes smaller and smaller as time goes larger and larger. The other one is called the force or the steady state response. Notice that this is exactly minus 1 to the power of n is the input. The only thing changed is the scale. So the input actually is scaled by 2/3 when passed through the system. So if we plot 2/3, so you see it is always the same value and is alternating. So this is the forced response. Now the sum of the transient and the steady state response becomes the total response over here. You will notice that in the beginning the inputs didn't go to exactly the correct value, but after in this example only after about 4 or 5 samples it stabilized to the final output. Here is still a little bit short of the the final output value. Alright, so this figure is a nice example to show how we find the steady state response and the transient response. Thank you.